Thank you very much to the organizers for inviting me, of course. And I changed the topic of my talk because today is Polynomial Day, so I thought it very fitting that I talk about my work with polynomials, especially polynomials having to do with NP-complete problems. So off we go. Here is a big picture overview of where we're going. We start out with some combinatorial problem, one that we know and love, like graph K colorability, partition, perfect matching, independent set, and off we go. We model it as a system of polynomial equations. And once we are there with that algebraic representation, there are a couple of things that we can do. The system of polynomial equations, of course, will either be feasible or infeasible. The underlying combinatorial property will either be satisfied or not satisfied. And so if it is satisfied, we can look at the Grosvenor bases and we can look at the algebraic representation of that Grosvenor bases and investigate whether it's polynomial size or exponential size. And also, what is the combinatorial interpretation of those polynomials? Similarly, if it's infeasible, if the underlying combinatorial property has no solution, we can look at Hilberts Nullstellensatz certificates of infeasibility. So there we are, and in both cases we can investigate. We can run computational experiments and we can investigate. So off we go. Let's look at a problem that we know and love, the independent set problem. Given a graph G, we ask the question, does there exist a subset of vertices of size K such that no two vertices are adjacent? So we are very familiar with this. And here we can see a sample graph that we'll be working with, and we can observe that vertices 3 and 4 are an independent set. And we can further observe, using our finely honed skills, that the largest independent set in this graph is of size 2. And the Greek letter associated with that is alpha G. And that will be used later. So off we go. We said that our overall structure was to take this combinatorial problem and model it as a system of polynomial equations. So again, this is something that we know and love. This is Lovász's representation of the independent set problem as a system of polynomial equations. So no problem at all, one variable per vertex. For every vertex, we have this polynomial, which says basically the vertex is either 1 or 0. The vertex is either in the independent set or not. And then for every edge, we have this, certifying that no two adjacent edges can both be in an independent set. And since we want an independent set of size K, we then can sum up all the vertices and say we want exactly K vertices to be in the independent set. So now we have a system of polynomial equations. Of course, it's satisfied if and only if the underlying graph has an independent set of size K. So here we are. Here's our trusty example, and here's the system of polynomial equations associated with the question of, does this graph have an independent set of size 3? And of course the answer is no. So in this case, we get to investigate the Hilberts Nullstellensatz certificate of infeasibility. And you can see here are the vertex polynomials, here are the polynomials associated with the edges, and here we have the question of, is there an independent set of size 3? So off we go. And let's refresh our memory as to exactly what Hilberts Nullstellensatz says. So from 1893, a trusty theorem that we still use today, given a system of polynomial equations, F1 through Fs, this system has no solution if and only if there exist polynomials, beta 1 through beta s, such that the number 1 can be expressed as a combination of those beta polynomials and those F polynomials. So if we have this algebraic identity, if it happens that we stumble across it, if this algebraic identity exists, we can be certain that the underlying system of polynomial equations has no solution. Because if there was a solution, if there was some point where all of these polynomials simultaneously, all of those polynomials simultaneously equaled 0, then what we would end up with is 1, equal to 0, which of course can't happen. So if we have this, then no such solution exists. So this is a certificate of infeasibility. This is a mini proof. If we have this, nothing more is needed. So here's an example. Here's a trusty system of polynomial equations, very simple. And if I choose to put these particular coefficients on those polynomials, if I expanded them out and grouped the coefficients together, you would very easily see that everything cancels out to 0 except the constant term, which is 1. So no problem at all. This is indeed a Nullstellensatz certificate of infeasibility. So off we go. We call this a Nullstellensatz certificate, and we want to measure the complexity. So we measure the complexity by the things that are missing. Of course, we have this. This is given to us as input. So we're interested in what we don't have. So we say that D is the maximum degree of those missing coefficients. That's the degree of the Nullstellensatz certificate. So off we go. Of course, it's useful to take just 1 second to say how we find those. So let's look. Here's a sample system. What we would do is guess the degree and create general coefficients of that degree with unknowns associated with the variables. Then we expand everything out. We group the like coefficients together. And what we then see is that these are linear expressions, so these have to sum to 0, except the constant term, which has to be 1. This gives us a system of linear equations, which we are then more than capable of solving. So if we are lucky, and if we have guessed right, that this happened to be the degree, if we guessed right, we could then reconstruct the certificate. Otherwise, we have to increment the degree and repeat. So that's just a short word about how we find these certificates. We won't really talk more about that. We're interested in what the certificates look like. So,
How does the complexity of finding a certificate compare with the complexity of just determining straight out if there's a solution?
There's going to be a mapping there, absolutely. Since the independent set problem is NP complete, we would expect the size of the linear system to be exponential so that it was not a polynomial time algorithm. We would expect the degree to be high if it is an NP complete problem. We would expect the degree to be low if it was a problem in P.
No problem that, but there's also only like a one-sided answer, right? Because you're assuming it's insolvable.
Yes, exactly. If it happens that the problem does have an independent set of size k, then you would have to iterate awfully high in order to really determine that no such Nullstellensatz certificate exists. There are well-known upper bounds for the size of Nullstellensatz certificates, so the algorithm will terminate. But obviously, you would be better posed to look for the Grosvenor bases, kind of alternate a little bit. Guess a degree, see if it works, maybe try the Grosvenor bases, that kind of thing, switch back and forth. But what we are interested in is taking a look at what the certificates look like. What is the combinatorial interpretation of these certificates? So here is our trusty example, and here is the polynomial which determines the size of the independent set. And you can see here I've decided to jump it to 4 just because I feel like it. But the important relevant thing is, so here's this polynomial, here are the edge polynomials, and here are the vertex polynomials here, and this algebraic identity does indeed sum to 1 if you put it into Maple or did it out by hand. But what's interesting is this, what we see over here. So what we see over here is that there's one monomial for each of the vertices, one monomial for the single isolated independent sets, and then there's one monomial for 1 and 2 and 3 and 4, indicating that these are indeed independent sets. So what you can see by looking at this certificate is that the degree of the certificate is equivalent to the size of the largest independent set, and that there's one monomial for each of the independent sets. So what we see here in the Nullstellensatz certificate is the full count of all the independent sets. And we have a theorem, of course, which says that. So the degree is equal to alpha g, which is our independence number, and it contains at least one term for every independent set. So off we go, investigating. So what is there more to say about this certificate? We've discussed and presented an interpretation of those monomials in full. But now we want to investigate these numbers. What do these numbers mean? Is there something combinatorial to be said about these numbers? So we can see that. We can answer that question really beautifully if we go to a different NP-complete problem that we know and love. And this one is the partition problem. Given a set of integers, can you split it into two sets such that they sum to the identical number? And off we go. Here's an example. We have a set of numbers, and we're going to split them into two pieces. Certainly, if I wish, this could be S. Certainly, if I wish, this could be everything else. A quick addition yields the fact that this is indeed partitionable. Fine. So we comment that this is an NP-complete. Yes, quite right. We allow repetitions here. Yes, yes. So off we go. Investigating. Very easy to see this represented as a system of polynomial equations. Very similar to what we had before. One variable per integer, and now one polynomial again per integer. Xi squared minus 1. Xi, of course, will be plus or minus 1, indicating one side of the partition or the other side of the partition, in the same way that the independent set meant in the independent set or not in the independent set. So off we go. And then, of course, we want these to sum to 0 because we want the partitions to balance. So nice and easy. Of course, this comes with a nice little proposition. This system of polynomial equations is satisfied if and only if there exists some partition. So here we go. Here we have a system of polynomial equations, and we ask the question, is this partitionable? And you can see that here we have 1, 3, 5, and 2. This polynomial here maps to this polynomial here. These polynomials here determine which side of the partition the integer is on. So with a quick inspection, we can convince ourselves that this is indeed not partitionable, just a quick inspection. So we expect this to be infeasible. We expect a Hilberts Nullstellensatz certificate to exist. So off we go, looking for it. And there it is. Just a nice, healthy disaster with much more complicated numbers. So first, let us look and see what we can glean about the monomials. So here is x1 squared minus 1, and a quick inspection yields that this has even degree monomials, and none of the monomials contain x1. Similarly here, x2, this has even degree monomials, nothing containing x2. Similarly here. So what we begin to see is that these monomials are a brute force iteration over all the partitions. This Nullstellensatz certificate is counting all of the partitions. Now, and of course, we were able to prove that. We have a nice theorem. Very large and cumbersome, but basically this says that this minimum degree certificate contains exactly one monomial for each of the even parity subsets and exactly one monomial for each of the odd parity subsets. Fine, very similar to what we saw for the independent set, but what about those numbers? That's what we were after next. So off we go, and I'm going to hone in on... Of course.
Kind of hard to parse.
Oh yes, it's yeah. Take your time. Take your time.
What do you mean by dense?
By dense, so the notion is what you have here is a certificate of the non-existence of a combinatorial property. So we expect that proof to be hard to verify because we don't expect NP to equal co-NP. So by dense, I basically mean dense with monomials. You could have a certificate that was of high degree, but it was very sparse, and so therefore still easy to verify. But because this is high degree and very dense with monomials, it takes exponential time to verify as well as calculate.
This means many monomials?
Many monomials. That's right, many monomials. Yes, exactly. Okay, so now we'll breeze on, and we'll just take another look. And now you can see the theorem reflected. Here are the even degree sets. These are all the even degree sets. And now here you see the odd degree sets. Degree 1 and 3, degree 0 and 2. So here in the certificate we see the theorem expressed. So now, as promised, we're after this number. What's the combinatorial interpretation of this number? How do we see the counting of the independent sets reflected in this number? So off we go. It turns out that we can take the underlying linear system associated with these certificates. We can massage them a little bit and make them square. So now here I have a matrix, which I call the partition matrix, and this matrix comes from that linear system. Fine. Now, if I wish, I could regale you with a brute force iteration over every possible partition. So I'm going to do that. So here are our numbers, W1, W2, and W3. And I stick W3 on one side of the partition. I can put both on one. I can put one on one, one on the other. I can flip them about, and then I can put both on the other side. Very entertaining brute force iteration. So if I wished, I could put signs upon them. Whoops, if I wished, I could put signs upon them. Nothing is certainly stopping me from doing that. The positive versus the negative. If I wished, I could then multiply all of those things together. No reason why I can't. I can then give it a name. But the interesting thing finally arrives for us. The determinant of this matrix is now equal to this partition polynomial. The determinant of this matrix happens to be to factor as the brute force iteration over every possible partition. So was that fluke, we asked ourselves? So off we went. We investigated one larger. This again comes specifically from the linear system. We can take the determinant and factor it, and again we see a brute force iteration over every possible partition. So that was the theorem that came out of this. Shmuel On, your colleague, I believe. And now we will take a look by Cramers Rule.
What's the rule for making that matrix?
Basically, you take the Hilberts Nullstellensatz certificate associated with the degree for that particular set of integers, and you perform some very simple manipulations, and some of the equations drop out, and it goes down to a square matrix. Yeah, just some massaging going from a non-square linear system to a square linear system. So by Cramers Rule, nice and easy. Here is our number, 34 over 693, and what we see is here is the brute force iteration over every possible partition for these particular numbers, and we apply Cramers Rule, and this is what we get, and that is indeed the 34 over 693. So each one of the numbers in that Nullstellensatz certificate comes from the counting of all of the possible partitions. So off we go, investigating more, because these were very nice. These combinatorial interpretations were very clean and very pretty, but that doesn't always happen. It doesn't always work out that way. So, given a graph G and an integer k, can the vertices be colored with k colors in such a way that no two adjacent vertices are the same color? No problem at all. Here's our trusty Peterson graph. 3 colorable, as we know and love. So now we want to represent this as a system of polynomial equations. So we're going to use a field k such that the characteristic k is relatively prime to the coloring number.
Nick?
Yes?
How about the degrees of this, in the Hilberts Nullstellensatz, the coefficients beta, I think you call them, they have a certain degree, so can you give the degrees a combinatorial interpretation?
You mean for the partition problem?
Yes.
Yes.
Because I think the partition problem should behave differently from the independent set problem. I mean, it's
Yes.
not as a difficult problem as the independent set problem.
Yes, absolutely. So if you cast your mind back, it was you had one monomial for every even degree set and one monomial for every odd set. So that means that the degree is going to be n minus 1 if it's even and n if it's odd. So in the case of the independent set problem, the degree of the certificate was alpha g, the size of the largest independent set. In the case of the partition, it'll be n or n minus 1, depending on the parity of n, because you're doing an iteration over every possible set. So just going back to see that, here, for example, n is 4. We have 4 integers. So the degree here is degree 3. n minus 1 is the size of the largest even degree set. And that will be true. So if this was odd, so now the degree here is n minus 1. This is the degree 3 is the largest coefficient. If n was odd, the degree here would be n. It would go all the way up to 5. Okay, so off we go. K colorability. Now, so here we have the encoding. We have one variable per vertex, just as before. We allow k colors, so k roots of unity, no problem. We're going to call this polynomial vi. This will come into play. We'll use this in a second when we explore a Grosvenor basis. And here we have for every edge. Now this polynomial here, it's easy enough to see that this polynomial here forces every vertex to take on one of the k roots of unity or one of the k colors. But this polynomial here causes each of the vertices to take on a different color. And that's easier to see when you realize that this polynomial factors thusly. And so we'll call that E of ij. And as before, this comes with a trustee theorem, saying this is feasible if and only if the graph is k-colorable. So off we go, investigating. And here's our trusty Peterson graph. This is indeed 3-colorable. And here you can see for every vertex in the graph, it is one of the 3 colors. And here we see for every edge in the graph, this here forces each of those adjacent vertices to share a different color. So this problem is feasible, so just for fun, in a very simple case, we'll look at the Grosvenor bases, and we'll see if the complexity of the Grosvenor bases can mirror some of the complexity of the combinatorial problem. So we look, and we refresh our memory, and we say a graph is chordal if every cycle of length greater than 3 has a chord, i.e. every induced cycle has length at most 3. So over here on our left, we see a graph with a lovely set of induced cycles. This graph is chordal. And over here we see a cycle, an induced cycle of length 4 that has no chord. So this graph is chordal, this graph is not. So off we go. And we have a theorem that says if the graph happens to be chordal, then there exists a polynomial time computable Grosvenor basis for the k-coloring ideal. And this doesn't surprise us because, of course, chordal graphs are going to be very easy to grapple with. So we expect easy complexity in the combinatorial problem to be reflected within the algebraic geometry. And I just comment that this theorem has a healthy number of authors on it. It came out of one of the MRCs at Snowbird, Utah. So let's take a look. Just visually, let's investigate what happens with this proof. So we have a particular polynomial, which we name SR. And here is a graph, and we comment that it's well known that every chordal graph can be iteratively constructed. And we're going to use that well-known iterative construction to build a Grosvenor basis, and that's kind of how the proof went. So we take a look, and if we wanted to iteratively construct this particular chordal graph, we could start with vertex 1 and this associated polynomial. Remember, that would just be xi to the k minus 1, or x1 to the k minus 1. And as we add an edge, we add this particular polynomial. As we add another edge, we add this particular polynomial. As we continue growing it, we add the associated polynomial. And by the time we get to the end, we have the chordal graph. And this is the Grosvenor basis, it turns out. So that was the theorem that came out of Snowbird. So now we've looked at Grosvenor bases. Now let's look at the Hilbert Nullstellensatz certificates. So We actually don't know very much about these certificates, surprisingly enough. For the partition problem for independent set, the counting to the algebraic geometry is clear. It's nice and clean, nice and clear. For graph K colorability, even for graph 3 colorability, it is a mystery. So we know that the degree grows in this nice, clean pattern. This doesn't bother us. 1, 4, 7, 10 in the case of 3 colorability. This makes sense to us. And degree 1 certificates have been explored. There is a known combinatorial interpretation of just degree 1 certificates. And it was done twice, one De Luera, Hiller, Malkin, and Omar in 2010. They described a covering of the graph in terms of directed edges. And they said if the graph had a particular covering of these directed edges, then it had a degree 1 certificate, and its non-colorability could be solved in polynomial time. So this was a new piece of combinatorics coming out of the algebraic geometry. In 2015, this was tightened a bit, and the directed edges were dropped, and Lee, Lowenstein, and Omar came up with an interpretation just based on 2 paths. So a 2-path cover, if your graph had a particular 2-path cover, it was a polynomial time solvable instance of graph 3 coloring, which was, again, new. Now, what about degree 4 certificates? The next most simple number. But it turns out that this remains an open question. The combinatorics here is not yet understood. So we do know, however, that there is a family of graphs that follows this pattern. It's the Michihara-Nizuno infinite family of graphs. And basically what they do is they start out with a series of graphs. Basically, they take all these graphs and they throw them in a bag. And these are called MUGs. Minimum unsolvable graphs, MUGs. And then they reach into the bag and they take 2 of them, and then they pick a vertex at random and join those 2 graphs using something, the Oyosh construction. So that's how they create an infinite family. And it turns out that if you apply that algorithm and you create an infinite family of graphs, so here we've done that, G0, we say, G1, G2, G3, G4, 10 vertices, 18 edges, 20 vertices, 37 edges, 30, 55, 39, 72, 49, 90. So we've constructed a little bit of this infinite family. And nicely enough, the degree starts at 1, then it stays at 4 for a little while, and then it changes its mind and it goes to degree 7. So here we see that pattern, but the combinatorics, what it's counting, what is it trapping, what the algebraic geometry is counting is not so clear. So off we go, investigating.
Are you saying those numbers are independent of which? You're saying there's not a unique one in each degree, or there is a unique one in each degree?
A unique one of what?
This infinite family of graphs,
which is constructed randomly. So this is just a particular.
Right. So I was saying, are those degrees independent of the random construction? Or are they based on a particular construction?
Okay, good question. The answer is I actually don't know. I can tell you that this particular series of graphs, which we constructed, you know, by choosing a particular random vertex, happened to work out this way. But as to whether the second graph, you know, is the first, each and every one of these has degree 1. That I can assure you. But does every n choose 2 combination go to degree 4? That I'm not sure of. And every time you add an extra graph, does it stay 4? Does it stay 4 again? And then does it always change to 7? That I can't be. Yeah. But it is rather delightful to at least have an example to work from, something to look at where we could try to count and experiment. So off we go. We've looked now at a nice variety of NP-complete problems, why not look at problems that are in P? With the exception, of course, of the chordal graphs. That was a problem in P. So we ask, given a particular combinatorial problem, does there exist some encoding such that the Nullstellensatz certificates have polynomial size? If the problem is in P, will we have an easy algebraic proof? So off we go. The Peterson graph is 3 colorable, as we know. Very easy to say. It's not too colorable. No problem at all. We all know that if a graph is not too colorable, it contains an odd cycle, and it won't bother us at all to realize that we can take that odd cycle and go directly to a Nullstellensatz certificate of non-two colorability. A problem in P to very simple algebraic geometry. And we can see it here. So here is the vertex 0, and we can see nice and easy. We can trot around the outside, a nice odd cycle, right? So we start with, we remind ourselves that for not two colorability, we have 2 possible colors, and here would be the associated edge polynomial. So we start with vertex 0. We walk along. We add the polynomial associated with this edge. Then we add the polynomial associated with the next edge. And we continue to trot around that odd cycle, adding and alternating our signs as we go. And it won't bother us to see that in the end, this is indeed a Nullstellensatz certificate. So from the odd cycle comes nice and clean algebraic geometry. A problem in P has a nice small certificate. Now, what about perfect matching? What about one of our favorite problems, our most favorite combinatorial problems? So here we have a graph. It has a perfect matching, no problem at all. We want to represent this as a system of polynomial equations. So every vertex, for every vertex I, we take all the neighborhoods. We want only to be incident on one matched edge. For every adjacent edge, only one of them can be matched, no problem at all. And here we have a graph which has an odd number of vertices. No perfect matching, of course. Why do I even bother to show you such a simple thing? Here is the, now notice I'm taking this over the complex numbers at first. And here's the certificate. A horrible disaster, not clean at all for a problem supposedly in P. But when we change the field from the complex numbers, when we change it to F2, this complicated certificate does indeed simplify very nicely. And that is friendly. We would expect that. Very boring. A graph G has an odd number of vertices. Of course there's no perfect matching. There is a degree 0 Nullstellensatz certificate. This doesn't bother us at all. Nice and clean. We would expect that. But what about even number of vertices? It's equally simple problem. It's equally known to be solvable in polynomial time. What happens then? Unfortunately, the graph, the degree of the Nullstellensatz certificate grows for the perfect matching problem, even over a small finite field, which bothers us to no end. So refresh your memory as to Tutt's theorem. A perfect matching if and only if for every subset U, the subgraph induced has at most U connected components with an odd number of vertices. So we can very easily build an infinite family of graphs around a set U that we can remove, leaving a series of odd components. This is the most simple infinite family of graphs with an even number of vertices that has no perfect matching. And alas, the degrees of those grow. Starts out at 1, grows to 2, grows to 3, up to 4. Not polynomial size. This is extremely annoying to us. So we leave the open question. There are 2 ways to pursue this. Is there an encoding that is cleaner or a finite field that works better, such that this nice problem solvable in polynomial time has a nice clean series of algebraic identities? Or is it possible to take these certificates and reduce them via some quotient ring? So we're looking at both of those things because we're determined that a problem in P should have a nice compact algebraic representation. So those are some open problems. All these results were taken from the following papers, with the including this one. This is the one to come out of Snowbird. All available on my website, of course. And thank you very much for your kind attention.
much. We have time for some questions.
I wonder, as for matching, if you have considered matching in bipartite graphs, it's not so difficult.
Yes,
Does the degree also grow there?
it does. It does grow. It does grow. It's very annoying. It's very annoying. Yes. So we're looking, trying to understand what combinatorics gets picked up that's not so good, and how could we maybe reduce it.
It would be very interesting. I mean, as we know, it's polynomial time. It would be very interesting to see that this particular system of polynomial equations is efficiently solvable.
Yeah, this was a surprising result. This was a very annoying result. This result did not, these experiments, I should say, does not correspond to our intuition. So we're working on improving one of the two, either our intuition or the...
The growth of the degree is proved, or is it just, I mean, you observe?
Experimentally verified. Yes, not proved. If it was proved, probably we would have much greater insight. Yeah, an open problem still. Yes, sir.
Counting three colorability is sharply hard. How does this reflect in but the equations are very special equations. They are not like even NP hard in terms of the Bloom-Fuchs framework. Do you know anything?
So it is, what you say is very interesting. So, of course, counting the number of partitions, counting the number of independent sets, also sharp P hard. And, of course, what we see in the Nullstellensatz certificate is a clear one-to-one matching of that difficulty. But it turns out that the combinatorics that gets picked up in the certificates of non-three colorability is not so clear. It's not so clear what it's counting. It doesn't, it's not counting the number of colorings. It's, for example, in the degree 1 case, it's not counting the number of colorings at all. It's counting the number of this particular covering, which was a combinatorial property that was not known before people started studying the certificates directly, which is just interesting. So there's hope, perhaps, of, well, there must be a combinatorial property to describe the degree 4 certificates, which will then indicate another polynomial time solvable class of non-three colorable graphs.
So does the certificates coming out of the bipartite cases, does it like have monomials iterating over all perfect matchings? Sorry, the perfect matching case.
Not so clear. Not so clear. Yeah, it's not so clear. Yeah. I am not sure what is happening yet, but it does not seem to be a brute force iteration over the perfect matchings. Yeah.
It's known that even for even the largest matching, the smallest linear programming extension is still exponentially large, and I think even the semi-definite program or even Lasser hierarchy and so on. But Lasser hierarchy somehow is connected with searching for certificates. So is there a connection between?
So you're quite right. You've stated it very clearly. There's a hierarchy having to do with the Lazard bound with semi-definite programs. Certainly with the matching, we have a sequence of linear algebra computations. So in the same way we have a series of semi-definite programs, we have a series of linear algebra sequences. The relationship between the two is not known. It's certainly, I'm aware of the results that you say. It is very interesting that the smallest linear algebra representation is exponential size. Certainly this representation is nice and clean, polynomial size, no problem at all. We have one polynomial per vertex, one polynomial per edge. Definitely we have a compact representation, but not a compact Nullstellensatz certificate. So maybe a proof between those, mapping those two areas is something to look into, but not known.
Okay, thank you again.